and you will receive that little message saying it's being recorded. Okay, hey everyone, welcome to the System and Programming Language Virtual Meetup. And the mission of this meetup is to create a learning environment for everyone to learn computer system in general. And that includes distributed systems, database systems, computer networking, security, and programming languages as well. And today is one of those special events that we invite a guest speaker to give an overview of a special database in the market. It's called TiKV, and it's a graduate program from CNCF, and it's a distributed key value store. So just a quick note, this database meetup, we focused on learning a college course called from Carnegie Mellon University, and it's called CMU 15445. It's an undergraduate level course on database systems. And in the past, our event has been focusing on presenting the course completely in Chinese. And I imagine in the future, the course will also be presented in Chinese. So if you have a hard time understanding Chinese, that's okay. We have another upcoming new event called DB Internals Meetup, and that will be completely in English, and that will be me and other co-hosts of this event, including Verity, Libo, Chen Chi, and Lin Wen, will be presenting this DB Internals Meetup for you. And that the main topic of that will be to cover each chapter of Database Internals by Alex Petrov. And that's a great book to learn databases and how it's being used in industry. All right, so today we have Nick here. Nick is a software engineer at Microsoft, and previously he served on the core team of Rust language while he was working at Mozilla for 5 years and then PingCap for 2 years. While he was at PingCap, he applied his knowledge of Rust into an application program called TiKV, and he worked on the Rust client of TiKV. And today's topic will be an overview of TiKV. What's the architecture? Why do we care about it? What's this whole new SQL paradigm? And Nick will also talk about the Rust programming language. I'm very excited about this. So now let me turn this stage to you, Nick.
Thank you, and thanks for the introduction. So yeah, I'm going to talk about TiKV. I'm going to start by telling you what it is, so I won't get too much into that on the intro slide. And I'm going to talk a little bit also about how it's implemented, which hopefully is of interest if you're following the kind of database implementation or the course or the distributed system stuff. I haven't made so much of a plan as to kind of like where I want to spend my time. So please kind of interrupt if you have questions, and if stuff is particularly interesting to people and you would like me to go into a bit more depth, then please just ask, and I'm happy to kind of like spend a little bit more time there. Otherwise, I will kind of like be skipping through stuff relatively quickly. Where are we? Okay, so at the risk of kind of repeating the introduction, so I'm Nick Cameron. I'm currently an engineer at Microsoft, and I work on Rust in DevDiv. Today I'm going to be talking about work that I contributed to whilst I was working at PingCap, which is where I worked for a couple of years before Microsoft. I worked mostly on TiKV at PingCap and a variety of kind of other projects. I should say that pretty much everything that I'll talk about today is not my contribution. I'm talking about the contribution of others. Here it's mostly stuff that was implemented before I even started working at PingCap, and it's stuff that I've kind of like carried on, but the carrying on bit is kind of in details that I probably won't touch on. If you'd like to get in touch, please do. If you're at Microsoft, I know a lot of you are, just get in touch on Teams. I'm happy to chat about whatever, or my Twitter and GitHub and email details are on this slide. Okay, so starting with trying to kind of like explain what TiKV is. So I think the easier way is to actually start with TiDB. Which is the relationship to TiKV will hopefully become clear as I talk. But TiDB is kind of like the PIMCAP's primary product, and TiDB is a new SQL database. Maybe like to talk about this kind of like in kind of like historical kind of fashion. So kind of the SQL databases are or were in the past typically run kind of like on a single node, and they support this extremely kind of like rich language SQL, and in part by design of that language, and in part in implementation, and a great deal just because they happen to be on a single node, you get some pretty strong kind of transactional guarantees, kind of guarantees about consistency and so forth. And at some point, people figured that this was all very nice, but we have too much data to fit on a single node, like way too much data. So this is kind of like, I guess, kind of the start of kind of like the big data era, or kind of like some of the kind of like early Web 2.0 stuff. And folk decided that kind of this having kind of like these strong guarantees and this really powerful query language was great, but it's no good at all if like your data physically doesn't fit into the database. And so there's this no SQL movement, which said, well, let's be distributed, let's work on like lots of nodes, and we will give up these kind of like strong consistency guarantees and this powerful query language in order to get that. Very good trade-off at the time. But given time to work on these problems, people were like, well, why can't we kind of have both sides of this? And so the new SQL kind of movement was, let's have these massively distributed scalable databases, but also let's keep these kind of like nice transactional properties, consistency properties, like this ACID transaction stuff. And so TiDB is one of these kind of databases. It's a kind of like massively distributed, scales across kind of like thousands of nodes, and is kind of very elastic, horizontally scalable. But it also supports like SQL. It's MySQL compatible. And it has very strong consistency guarantees. It's an industrial strength database, and it's kind of a product that PINCAP have been selling for some time now. It's been really stress tested by some like really huge clients using it for really like big projects. So there's a few of the bigger names here, but this is really only kind of like scratching the surface. Kind of Bank of Beijing, Bank of China, Xiaomi, Jihu, Meituan, China UnionPay, Mobike, JD. It's also been used by Square and Shopee outside of China. So it's a kind of like, it's a very serious database, right? This is not kind of like an academic experiment or kind of like a toy open source project. This is like a real product. And yeah, kind of tens of thousands of nodes. It can be geo-distributed across multiple data centers. The most recent statistics I could find were for like tens of terabytes, but I'm pretty sure there are much bigger clusters than that now. And I couldn't find numbers on kind of like transactions per second, but lots. I remember some of the stats from when I was working at PINCAP, and it's kind of, we're dealing with like a really large number of transactions in parallel on these clusters. So implementation wise, TiDB has kind of like this coarse layered architecture where it has kind of a stateless front end, which handles kind of like the SQL processing, and kind of a storage backend. And TiKV is there are multiple possible storage engines, and TiKV is the original. Well, not actually the originals in the first, but kind of the for the longest time was kind of like the only one, and is probably the most important one at the moment. So TiKV is kind of the layer of TiDB which handles the kind of like the distributed systems nature of things and the storage nature of things, but not the actual kind of SQL layer. Okay, so before I kind of like get into TiKV in a little bit more detail, I'll just say one last thing about TiDB, which is kind of like put it in a bit of context within the kind of market of databases. So I said already that it's a new SQL database. So to be more precise about that, like it has an SQL interface rather than kind of like a key value interface. In particular, it's MySQL compatible. Some similar products are Postgres compatible, or are just kind of vaguely stick to the SQL standard, whereas TiDB is compatible with MySQL. And like I said, it's distributed, and it's built from scratch to be distributed. Some databases are, they've taken an existing implementation on one node and tried to extend that to work on many nodes, kind of like, so that the distributedness is kind of like bolted on after the fact. And I don't kind of want to get into details about kind of what happens there, but it doesn't work so well. It turns out that if you want to be a distributed database, you've really got to be distributed first, and not a database first. TiDB, it scales automatically, so the user is not concerned with manually sharding their data. So it looks just like a single node database. All the kind of like distributed stuff is abstracted away. I mean, that's not quite true, because you have a whole bunch of dials and knobs you can configure, which you wouldn't have if there were only one node. But when you're when you're writing an SQL statement or whatever, you don't have to consider sharding, which is in contrast to some distributed databases, especially those it seems that are adapted from kind of like single node databases, where you actually have to say, well, this data lives, or this table or these rows live on this node, and these other ones live on these nodes, or whatever. TiDB markets itself as an HTAP database. It's a hybrid transactional and analytical processing database, which is to say that it can do both kind of like the OLAP and the OTAP kind of functionalities. So you only need kind of like one database to do both the kind of like online kind of SQL queries, but also the kind of analytics stuff that you might only run kind of like once a day or once a week. And having multiple backends really helps with that. You can have kind of like a column-oriented backend rather than using TiKV as a row-oriented backend to make the kind of the analytics stuff more performant. TiDB is available both kind of like in self-hosted and cloud flavors. A lot of databases are kind of like one or the other. And finally, TiDB is kind of an entirely open source product. It's developed in the open, and kind of contributions are welcome as well as having kind of an open source license and you just being able to download the source code. Okay, so that's just some context of TiDB, which is not what I'm here to talk about today, but just to kind of like tell you about, that's kind of like how TiKV came about. And this is actually kind of a good point to stop if anyone has any questions so far.
Nick, when you say TiDB is distributed, do you mean it's geographically distributed?
So when I'm saying distributed, I mean that it runs on multiple nodes. It's a distributed system, as opposed to kind of like having a single database server. You can actually run it as geographically distributed as well. So that's kind of like a multiple data center setup. That's something that was working just as I kind of like left PinkUp. So I don't know exactly the status on that, but that's an area that's being worked on.
What's the transactional isolation level does it support?
I'm going to talk about that stuff with respect to TiKV, and that will apply equally to TiDB.
Awesome.
But to give you a quick answer, it's snapshot isolation, but I'll talk about that in a bit more detail when we get into talking about TiKV.
Great, thanks.
I have one question too.
Yep.
For the auto scale, how you when you auto scale, how you decide which load need to put in?
Sorry, could you repeat the question?
The details about the auto scale, just curious. How you choose which node you will expand or?
So I'll talk a little bit more about that when we're talking about TiKV, because where the data lives is kind of TiKV's job rather than TiDB. And I'll try and kind of like, once I've talked about that a bit, I'll try and get back to your question. So if I don't cover it, like when I'm talking about TiKV, please ask me again. Okay?
Sure, thank you.
Okay, so there's a question on chat which is about Rust, and I have a whole section about that. So I'll get back to that later as well. Okay, so I'm gonna carry on now and kind of tell you about TiKV. So TiKV is a key value store, which is to say that it's simply a mapping from keys, which are a bunch of bytes, to values, which are a bunch of bytes. So it's kind of like a hash map, but persistent, rather than kind of like being kind of like an SQL type database. It can because we're just storing keys and values, you can store like billions of them on a single node, and of course many more when we're distributed. The API that the key value store has is kind of what you would expect from something like a hash map. It's got kind of like get and set and delete kind of functionality. There's also kind of like more advanced functionality to kind of like scan or to read kind of ranges of values, or to kind of like scan for particular values rather than getting just one. The API as well comes in kind of like both raw and transactional flavors for TiKV. Raw means that you literally just get access to a mapping from bytes to bytes, and there are no transactional guarantees. And obviously you can get various kind of like inconsistencies and conflicts that way, but it's kind of like the lowest level way to interact with the store. The transactional API means that you deal in transactions rather than single kind of like requests to get or set a value. I'll talk a little bit more about what that looks like later on. The kind of like what a key thing about TiKV is that it's a distributed system. Okay, so it's not just kind of like a single node database. It's what gives TiDB its scalability. And its distributed nature means that it's also durable, right? Like it means that you can lose a node, and that node could like literally be set on fire. Okay, the hard disk could die and disappear in smoke, and you still have like another copy, and you won't lose your data. And it also means it's fast. So this doesn't really mean kind of like an individual transaction, but it means that when you're in a situation with huge numbers of transactions, all those transactions can still complete really quickly. So as I said before about TiDB, TiKV is transactional, and it gives you these strong ACID kind of consistency guarantees. So this is kind of interesting. So when I talked at the beginning to give some kind of like historical context, I said that kind of like the NoSQL movement abandoned both the query language aspect of SQL, but also the transactional guarantees. So TiKV is a database that doesn't have the query language. It's a key value store, but it does have transactions, and it does have these transactional guarantees, which again I'll talk about now. So the guarantee that we offer is snapshot isolation. So that means well, I will explain later on how it means that we kind of like whenever you read at a particular timestamp. But if you continue to read at that timestamp, you will continue to read the same data. Okay, so just because another transaction happens, you'll still see kind of like a consistent view of the data that you're reading. So this is the repeatable read property. There are guaranteed to be no write conflicts as well. It's not quite as strong as proper serializability, because for serializability you have you can't have write skew, but with snapshot isolation, your transaction could write data based on an old value that you read. It's also has the linearizability property as well, if you're interested in that. TiKV is written in Rust. I've got a whole section next about kind of like what Rust is if you've not used it before, and why it's suitable for database development. So I'll skip this just for now. And it's open source. So not only is it developed in the open, but the project is managed in the open, and the project itself is owned by the Cloud Native Compute Foundation, CNCF, of which TiKV is a graduate project. Okay, so before I get to this slide, I feel that I kind of like missed something a little bit earlier, which is that I said that TiKV exists as the backend to TiDB, but TiKV can also be used as a standalone product in its own right. You do need a client, and I'll show, as you do with many databases, and I'll show kind of like what that client has to do. Yeah, you can use it kind of like as directly as a key value store. You don't have to use it within TiDB. So you could use, if you just need a key value store for your project, you can just use TiKV, or perhaps you're developing a product that like, you know, similar to TiDB, where you need kind of like a back end to handle kind of like distributing data and storage, and so you can abstract that all away by using TiKV. Okay, so similarly, like I did for TiDB, I just want to kind of like put TiKV, give some context, kind of its place in the market, and so on. So this time the database is a pure key value database. We don't have an SQL interface, and unlike something like MongoDB, it's not kind of a document database, or we don't have kind of like a tree structure to data or anything. The values in TiKV are opaque to TiKV. The data stored in TiKV is durable. It's written to disk, so that's in contrast to many key value stores, which are used as caches, which are just in memory databases. And as I said about TiDB, TiKV is a distributed database. It's able to kind of like scale across nodes. And again, like you don't, as a user, you don't need to worry about sharding the data manually. Sharding the data kind of happens automatically as part of the way it works. It doesn't work as an embedded database. It kind of like it's a database server, and you need to interact with it using a client. As I said already, it has strong transactional guarantees. You could argue that it has the ACID guarantees, and kind of because of that design decision, it's not there's not a prioritization of high availability. So you can lose some nodes, but you still need to have a majority of nodes accessible in order to be able to keep writing to the database. Otherwise, you could not maintain the ACID guarantees. So it's not as highly available as some NoSQL databases, which are willing to let data become inconsistent in order to have kind of high availability. It's in part because it's not an embedded database, because it's kind of uses the classic database as a server kind of model. It's not intrinsically tied to kind of like one language or runtime or whatever. So I've said that it's implemented in Rust, but you don't have to use it from Rust. You can use it from any programming language you like, as long as there's a client for TiKV that's available. And there are currently clients for Java, Python, Go, Rust, C, and it's relatively straightforward to bind one of those clients to whatever language you like, or to write a new client if that's what you want to do. And again, it's an open source project compared to many databases which are proprietary. Okay, so and again, probably another good break in the proceedings to ask if anyone has any questions about kind of like what TiKV is.
Actually, just curious, like when you say distributed, you mean it's like hash partition or range partition, or customer can choose like whatever like partition strategy you want?
It's range partitioned. So because TiKV supports kind of efficient queries over ranges and scanning queries, it has to be range partitioned. Like hash partition doesn't work if you want to offer that kind of API.
Okay, that makes sense. Because I was just curious, because I also noticed some other similar product like CockroachDB, they also use range partition.
Yeah.
I have a question about scaling.
Mm-hmm.
Let's say if you want to scale the key value store and you want to add more nodes, then I guess you need to move some nodes from previous node to the new node.
Yeah.
Yeah, and for that part, I'm wondering, how do you do the move?
So I'm not entirely sure, I must admit. So as I'll kind of like explain a bit later, the very kind of like lowest level of this stuff is that it's stored on disk using RocksDB, like using LSM tables. And I believe that you can simply kind of like copy that kind of like low level data to move it between nodes. I don't think you have to go through the kind of like the high level interface. I do know that this happens automatically, so I'll go with the architecture in a minute, but basically there are nodes called PD nodes, which are in charge of handling shard management. and will do that, move the data for you like that. So it's managed by the PD software. You don't have to do it manually, and I'm not exactly sure how that's implemented. Sorry.
Okay, thanks.
Okay, cool. So I'll move along. So TiKV is implemented in Rust, and I want to talk a little bit about Rust because it's what I work on now and have worked on a lot in the past, and I'm kind of passionate about the topic. So Rust is a programming language. I used to always say it's a new programming language, but it's not that new. But I guess it is compared to like C++ or Java or whatever. It's kind of like two highest priorities are to be fast and safe. Fast means that it's kind of like a low-level language like C or C++. The abstractions it gives you are zero-cost abstractions, i.e. that means that you don't pay, if you don't use the abstraction, you don't pay the cost of using it. And if you do use the abstraction, it is kind of as efficient or more efficient than what a person could reasonably write by hand. So this is a similar kind of principle to C++. In particular, this means there's not a garbage collector, and so you never have garbage collection pauses, which can kind of like kill your latency. Safe is both kind of a kind of a general principle in that the various features in the language and kind of like the libraries and stuff are designed like to be safe to use. But there's also kind of like a more precise principle, which is around memory safety. So as opposed to kind of like writing C or C++, Rust is a memory safe language, which means you never have to deal with errors like use after free or dangling pointers or buffer overruns, which are kind of like a huge category of exploitable security errors. So kind of like before Rust, you had kind of like the choice. Either you kind of use a garbage collected language where memory management happens automatically and at runtime, but you pay the cost in having kind of garbage collection pauses and having to have kind of a real heavyweight runtime can like slow down allocation as well as kind of like deleting memory. Or you have something like C++ where, or C or C++, where you allocate and free the memory manually yourself, but like you're at risk of making errors when doing that. And in fact, it's really easy to make those kind of errors, almost impossible not to, in fact, without tooling. And even with tooling, it's pretty difficult. Rust kind of like breaks that dilemma, I guess, by saying, well, you have to, memory is managed kind of manually in the sense that there's no garbage collector, but the compiler handles it. So the type system enforces memory safety. So this means that you get memory safety, which makes you much more productive because you don't have bugs. It makes your code more secure. But you don't have garbage collection. You don't have kind of like a heavyweight runtime, which means that your code is fast. Nothing's ever free. The downside is that means the type system in Rust is kind of complicated, and Rust has a somewhat steep learning curve. And sorry, a question from the chat is, can Rust still keep fast and safe when using FFI to call other language code? So fast, yes, or at least as fast as the code you're calling. You know, if you call some other language and it just chooses to sleep for 10 minutes, then it's going to slow your program down. Nothing you can do about that. But assuming the FFI of Rust is very fast. Safe, not necessarily, because of course, you know, if you're calling C, then C isn't able to talk. The the Rust compiler doesn't know what's happening in the C code, and so the C code is free to do anything and can break things behind Rust's back. And in fact, you can actually do this in Rust as well. And what you have in Rust is you have kind of unsafe blocks, and within an unsafe block, you are kind of manually responsible for enforcing the invariants, which would usually be enforced by the compiler. So essentially, you have to make sure that you delete the memory yourself. And so this is kind of like an escape hatch in Rust, and all kind of like FFI work talking to other languages has to go through this escape hatch. It's always unsafe code. And this has kind of like, obviously this means that there can still be bugs in your program, but you know, that's kind of like a fact of life. At some point you need to interact with the outside world, and you have to kind of like accept that you can have these kind of bugs. But what Rust lets you do is it lets you minimize the surface area of your program that is vulnerable to these bugs, and that's extremely powerful. Okay, so Rust is beginning to be widely used at Microsoft. There's a bunch of projects across the organization which are using it. Security folk in particular are especially keen for people to use it. So if you are if you also work at Microsoft and you are interested to use Rust, then you know it's definitely something that you're able to do if it's a good fit, and you can talk to me about that if you need more information about it. Rust is also developed at Microsoft. I'm paid by Microsoft to develop Rust, as are kind of like the rest of my team and several others at Microsoft. So you can consider Rust as an alternative for C or C++. Kind of a lot of places that you would use C are good candidates for using Rust, because presumably you're using C, C++ because you need the low levelness, so you need the performance, and Rust gives you that. It also gives you memory safety, and so this is a huge bonus. So you know, if you can use Rust in one of these places, then it's a good idea to do so, basically. You would also consider it as an alternative for kind of a high-level language like Go or C#. You know, if you're using this language and notice that kind of like performance is an issue, and that you're thinking that you need kind of like lower level control in order to get back some of the performance that you're missing, then using Rust is a good thing to use in this situation, because you get to keep the safety properties that you have from using these managed languages, but you still get the extra performance. You can't always use Rust. Interaction with other languages, you know, if you've got kind of like a code base you've got to work with, then you know, interacting with the existing code may be difficult, or more difficult using Rust than some other languages. Sometimes it works if you've got a very well encapsulated API, and especially if it's a C API, then Rust interacts quite well with it. But if you've got like a lot of C++ code, not so easy. Okay, so I think Rust is particularly well suited for database implementation. So as well as just being fast, and databases always want to be high performance, because they are kind of like really key parts of the software. They also always want to be really safe, because they're such fundamental parts of the software, because they are protecting like your data, which is, you know, the most important thing to protect. Kind of like safety, security is really important for databases. Databases also like to have kind of like low-level access to the disk, low-level access to memory, do their own memory management, that kind of stuff. And that's possible in Rust in a way that it isn't in most managed languages. Finally, like particularly for a distributed database, you're going to have like a lot of network communication. And so to do that efficiently, it's nice to be able to use kind of async IO, which Rust has in the language, and is kind of like a strong point of using the language. Okay, so that's kind of like my chapter on Rust. So it's another kind of chance to ask some questions before I kind of like dive into the implementation of TiKV.
Hi, Nick. Thanks for your sharing, and it's very impressive. I have one question about the Rust, and
Yep.
the community of Rust is like iteration is very fast. And how can you deal with the fast iteration of the Rust language with your like the somehow stable version of the TiKV? And also, how can you deal with like the slow like compile time in Rust during your daily development?
Sure. So I think the thing about the rapid development of Rust is that backwards compatibility is such an important thing for Rust that the rapid release schedule is purely positive. So there is very, very rarely are there ever any breaking changes in stable Rust. This has happened probably less than a dozen times in the since we released 1.0, which is 6 years ago now. Yeah, 6 years ago. And so even though you're getting a new version every 6 weeks, nothing breaks. Okay, so you might be getting some new features, and if you want to, you can use those new features, but of course you don't have to. And because of the backwards compatibility guarantees, nothing breaks. So that's great. You don't need to worry about the fact that there's rapid releases. Compile times, if you're used to Go, compile times in Rust seem very slow, and you probably need to kind of like adjust your development kind of methodology, I guess. If you're used to kind of C++, I would say that compile times in Rust are kind of rough for the same amount of code, kind of like roughly on par with C++. So there's not too much to deal with. Like I've been using Rust long enough that I'm just kind of like used to the compile times. It would of course be nicer if compile times were much quicker. Like if we could have the same compile times Go have, that would be obviously better. But we don't. In practice, you get used to it. It's just kind of like part of the trade-off. So
okay, makes sense. Thank you.
Okay, cool. So I just want to check that I answered Van Zhang's question. So like in terms of kind of like what are the reasons and concerns to kind of like have chosen Rust to develop TiKV, like the primary reason is performance. Like it's such a crucial kind of like building block for TiDB that performance is absolutely critical, and they made the call that they could not afford to lose kind of the percentages of performance that you would lose by using something like Go instead. In particular, it's really important for databases to be low latency, and if if you've got those long garbage collection pauses, then you can never really be sure about that. And like I think rather than using C or C++, kind of like the safety of Rust appealed, and the fact that it's just easier for people who are not experienced system programmers to write Rust is a real kind of like point in its favor as well. I think there were in case it's not clear, like TiKV started a long time before I joined PingCap, and so the decision to use Rust was made years before I was working there. And in those times, it was quite a risky decision to use Rust. I think now it's kind of like matured a lot and is much more popular. So I think that was quite a high risk decision that they made to choose it. And I think, concerns would be about finding people who are able to work productively on Rust primarily, right? Just because of its level of popularity at that stage. And another question from Eric is about the fragmentation of the async ecosystem. I don't think that that's impeding the development of the language. Like, the language continues to develop and continues to do so quickly. I think it's suboptimal for users, and kind of my main work on Rust at the moment is actually to address that, and try and make the kind of, there are always reasons why you might want to have different async runtimes. Okay, like that's never going to disappear, and so I think there's always going to be a choice of multiple runtimes. But like, we want that to be one ecosystem with this choice you can make where you absolutely need to get the last kind of like little bits of performance out of it. And so like, we have a goal to improve this, but I don't think that it's kind of like a huge deal for most of the language. Is that a kind of good enough answer? Okay, there's a sure in chat, thanks. Okay, so I'm going to move on and talk a bit about the implementation of TiKV. So this is just this is kind of like a very high level looking at the architecture of what a TiKV cluster looks like. So on the bottom right, we've got the TiKV nodes. We've got 6 here. You might have 6, you might have thousands. It's scalable like that. Above that, you've got some PD nodes. And so PD is the placement driver, and PD has 2 jobs. One is to manage sharding, and so in particular, this mapping of which physical node and data lives on. The second job of PD is to supply timestamps. Timestamps are really important how TiKV's transactions work, and PD works as a timestamp oracle. Okay, so then to the left of the TiKV cluster in red, we have the TiDB nodes. Now, you might not be using TiKV inside of TiDB, and so these might not be here, but you do need some kind of client. And if you're going to get the most out of running like the distributed database, you're probably not going to, that's probably not going to be just like a client on one machine. So it's likely you're going to have like some kind of like client cluster as the front end to your application. On the far left, we've got kind of communication with the rest of the application using MySQL. And it, again, like if you're not using TiDB, then you're not going to be using the MySQL protocol. You'll be using something kind of like more custom. And then the big blue arrows, as I mentioned, are kind of the timestamp information, data location, kind of moving between PD and both the client and TiKV nodes. So I should say, by the way, that what the client does here is quite a lot. Okay, as I go through this implementation of the transaction system, you'll see that the client has quite a lot of responsibilities, but the language clients as they exist today, that abstracts all that away from you. So as an application developer, you have a much more abstract view where you're just dealing with transactions over keys and values, rather than kind of like doing this kind of like complex protocol that I'm going to talk about shortly. I've missed one. Here we go. Okay, so this is about sharding. So shards in TiKV are called regions. So here we've just got 3 regions. And as I said a bit earlier in response to a question, we use kind of range based sharding. So you might have all the keys between 0 and 1,000 are in region 1, 1,000 between 1,000 and 2,000 are in region 2, between like 2,000 and 3,000 are in region 3. right? So your data is split into ranges, and each of those ranges is a region. And then each region is replicated across multiple nodes. So in this diagram, we have 4 TiKV nodes, nodes A, B, C, D. And you see like region 1 is replicated, nodes A, B, and D, and so forth with the other regions. Note that there's always kind of like a leader node and 2 replica nodes. So these are not kind of like homogeneous nodes. This is leaders and followers. Sorry, I wanted to say one more thing. Oh yes, so this diagram is just kind of obviously for illustrative purposes. In real life, you're likely to have kind of like thousands, tens of thousands, hundreds of thousands of regions. Okay, so there's in a proper cluster, there's lots of regions. Your obviously kind of how many nodes you have depends on the scale of your cluster, but the level of replication is fixed. So even in real life, and even when you have tens of thousands of nodes and potentially millions of regions, you still only have kind of like 3 replicas of each region. You can actually kind of like customize that number. You could, if you want, to have like 5, but it's not a number that grows as the cluster scales. That's a fixed number. And there was a question about where does the transaction coordinator live? I guess in the client, in the kind of like I mean, it depends exactly what you mean by transaction coordinator. There is not kind of like a central transaction coordinator node as such, but kind of like the code that is coordinating a transaction is the client code. Hopefully that will be a bit more clear when I explain the transaction protocol in a couple of slides. Okay, so looking at an individual TiKV node, it has basically kind of like a layered architecture. So you have the transactional API, which is the API kind of like presented by the TiKV node. That is implemented using multi-version concurrency control, and that sits on top of an implementation of the Raft consensus algorithm, which is responsible for replicating that data across the replicas, as we just saw the replicas of the regions. And at the bottom, you have RocksDB, which is used to persist data to disk. And I'll go through each of these steps kind of like in turn as we go along. There's also a coprocessor module in TiKV. So this is really interesting. I'm not going to talk about it in detail in this talk, but the coprocessor, it lets you move code close to where the data lives. So if you imagine you've got kind of like a select statement where you want to like sum the values of a single column across, say, 1 million rows. So if you did this in the really naive way, right, like you'd get your client nodes to lower the select statement into a query. So you'd get kind of like send a request to the nodes to get the value from this particular column, and then return all those to the TiDB node and sum them all up. Okay, but that potentially means, you know, if you're summing across 1 million rows, that means you're sending 1 million pieces of data from the TiKV cluster to the TiDB node. It's much more efficient if, you know, if say those 1 million rows are distributed across 10 nodes, each of those nodes adds up the columns locally, and then you're just sending 10 values back to the TiDB node, which can add them all up at the end. And so that's what the coprocessor does, and it's actually a customizable coprocessor. You can kind of like plug different ones in, as well as kind of the TiDB SQL coprocessor, and it's a really kind of like neat idea. but that's all I'm going to say about it in this talk. Okay, before I move on, there's a couple more questions. TiKV uses a multi-raft system, not just the kind of like vanilla raft. And a comment about using percolator, which I'm going to like talk about next. Oops. Okay, so the transaction system. I'll kind of explain TiKV transactions now. So TiKV transactions are collaborative in that the server API does not talk about kind of like transactions. You can't just send RPC messages to the server, like start a transaction, The client is kind of part of the transaction protocol. And it has to kind of like collaborate with the various server nodes to do that. And in that sense, the client is the transaction coordinator. The transaction protocol you use is a two-phase commit algorithm. It's based on the percolator algorithm developed at Google some time ago. Before I get into the details of transactions, I just want to say that the way the data is stored is we use a multi-version concurrency control system, which means rather than storing like a single value for each key, which is the most recent value, we store a history of values at various timestamps. And these can be garbage collected at some point, but that's a detail. So yeah, although it looks like you have a single value, the implementation will have multiple values, and I'll explain exactly how that works in a second. And as I've been hinting at already, kind of timestamps are really important for how this works. So there's two timestamps that I'm going to use in this talk. There's the start timestamp, which is the time when you begin a transaction. And there's the commit timestamp, which is the time when the transaction is committed. Both of these timestamps have to be retrieved from PD. And I'll show that as part of the transaction in a sec. Okay, so multi-version concurrency, this is kind of how it works. So imagine we've got kind of like a bunch of keys. Sorry, so just to the conversation in the chat. So there's a link to the percolator paper. It's a really great paper. I recommend you read it. It's a really good read. And the main ideas of percolator, I'm just kind of describing starting right now for the next few slides. Yeah. So okay, so imagine we've got like a bunch of keys, K1, K2, K3, K4, K5, and we write values. Each of the dots on these lines are a value that we write to a key at a certain time point. Time is kind of flowing from the left to the right of the screen here. And then we want to read the state of these keys. So we want to read a snapshot of the database at a specific time t, which is the red line. So in order to do that, we kind of like have to look backwards through time to find the most recent value that's been stored for that particular key. So that's going to be the red dots, the most recent values for all these keys. And that's the values that are going to get returned when we do a read at time t. Okay, so this diagram is a sequence diagram for the transaction protocol. So we can see there's three classes of actor. So there's the client, which is the kind of transaction coordinator. As I said, the PD nodes are just a timestamp oracle, and then there could be any number of TiKV nodes. In this example, there's just two to simplify things, but it could be lots. So I will say like rather than think of these as TiKV nodes, these are TiKV regions. So this assumes that there are 2 regions. And so there could be, anywhere between 3 and 6 TiKV nodes involved in this process, but we're going to abstract all those away and just deal with the regions at the moment. Okay, so the client begins a transaction. So the very first thing the client has to do is it has to talk to PD and get the start timestamp. Once it's got that start timestamp, then it can begin building up the transaction. So a transaction is the sequence of reads and writes. Reads are executed straight away. So if you want to read a key, we have to send a request to a particular TiKV node to read that value, and we read at the start timestamp. Okay, so this is really important that all the reads are done at the start timestamp. Writes are buffered locally. We don't execute the writes straight away. We just build those up in a buffer. When the application is done with the transaction, we're at the end of we're at this end label on the left-hand side. So that's the point where we've built up the transaction as we need. And then we start the first phase of the commit process. So first of all, we send pre-write messages, and we send pre-write messages to every node where there's a write. So if you read from a node but didn't write, then we don't need to worry about that node anymore. But every write has to be sent as a pre-write message to the correct node. And we have to, the client then waits to get replies. And of course, it will resend if a message gets lost and there are timeouts and so forth. But hopefully we get all the pre-writes back, responses to all the pre-writes back. If any of those pre-writes fail, then the transaction fails and we roll back the transaction. Assuming all the pre-writes succeed, then we can continue to phase 2 of the 2-phase commit protocol, which is sending a commit message. So the first thing we do is as soon as the client has all the pre-write responses, is that it gets a commit timestamp from PD. And this is the timestamp at which all the writes in the transaction become visible to other transactions. Okay, so the client can then send the commit message with the commit timestamp to all the TiKV nodes. Right? Kind of like a slight optimization to this is that actually we select one of the keys that we write to be the primary key, and the node on which that key lives is the primary node, and that key is the single source of truth for the whole transaction. Okay, so if we look at that transaction, we look at that key, and that key says that the transaction is committed, then we consider it committed. If we look at that key and it says that it's rolled back or not committed, then that transaction is not committed, no matter what the other keys say. So the client will, first of all, try and commit that primary key. And as soon as the primary key succeeds, then we can return success to the user. All the other nodes, they can be committed asynchronously, because even if they fail, there's recovery mechanism built in, which means that the transaction will still be okay. So there's a question in the chat, does pre-write lock the key? Yes, and I'll get into a bit more detail about what happens with each of these actions in the next few slides. So this is kind of the the architectural view of what's going on with the transaction protocol. The recovery protocols are kind of interesting. So this is in response to another question from chat, is how do we recover if the secondary commit fails? So basically, if you try and read and you find a key that's still and the key is locked, i.e. it was the pre-write has completed, but there was never any commit message, then first of all, there's a timeout, so that you wait to see if the transaction will complete naturally. If it doesn't complete in that time, or you read it after that time anyway, then you will start this recovery procedure. And the recovery procedure basically just finds, you have a reference to the primary key, and you look at the primary key to see what's happened. If the primary key says the transaction committed, then you can update the other keys and read from them. If the primary key was not committed, well, you've already passed the timeout, so you roll back the entire transaction. Okay, so so there's another question in the chat. Is it looks like two-phase commit plus transaction coordinator at the client? That's correct. And what part is related to percolator? And I mean, that's exactly this, what the percolator algorithm is, basically. Percolator is a little bit different. So the percolator paper has some stuff that's not related to the transaction protocol, which is not relevant to TiKV, but the transaction protocol part of percolator is pretty much the what is happening here. Even the kind of like the MVCC representation or the implementation of the nodes is basically percolator. Where percolator is a little bit different is that it doesn't have a timestamp oracle. It uses basically you throw money at the problem because you're Google, and you use kind of GPS and atomic clocks to get a really accurate timestamp without having to have a timestamp oracle. Whereas we TiKV has a timestamp oracle in the PD cluster.
What you just described in Google, it's called true time, right?
Yeah, so true time is the system using like atomic clocks and GPS and so forth.
Okay.
Does that answer the question of like how this is related to percolator? Okay, yes. Okay, great, cool, thank you. Okay, so I just wanted to do a time check because it's 7:10, and I said I'd be finished by now and we could do some questions, but I've been answering some questions as we go along, and I think I have maybe like another 10 slides or something, but these are basically just details of transactions. So I can skip the details of transactions and have a bit of time for questions, or I can go through the details and maybe have less time at the end. Is there a preference? Okay, one vote for details, another vote for details.
Guess we'll just go details.
3 votes for details. Okay, details it is. Okay, so the next few slides describe basically how the transaction protocol is kind of like implemented on the server nodes. And I'm going to first of all talk about kind of like the MVCC representation, and then I'm going to talk in a little bit of detail about the actions like pre-write and commit and read and how they use these representations. Okay, so the underlying storage that we have here is just keys and values. And so we need to somehow encode the MVCC concepts, which is kind of like versions and locks and multiple versions for a single key, into the underlying simple key value storage. So this is how it's done. Okay, first of all, we have to have this concept of column families. So a column family is basically just a separate database. In the sense that like the domains of keys are like disjoint. So if you have kind of so TiKV, for example, uses 3 column families, and that means you can store whatever, some key and with a different value in each column family, and each column family can be configured separately as if it were an independent database. The only difference between kind of like a column family and actually having a separate database is that you have atomicities. So you can write to multiple column families in one atomic transaction. So as I was saying, like TiKV has 3 column families. There's the default column family, which is where we store the actual the user values, the values that the user is trying to store for a particular key. There's the write column family, which stores metadata about when data has been committed. And there is a lock column family, which is used for locking, for locking individual keys. Okay, so the default column family, we use as a key in that column family, we use a combination of the user key and the start timestamp. And what we store is the value. And we write this value during pre-write, as we'll see shortly. Okay, so the write column family is probably the most interesting. So again, we store the physical key in the write column family is a combination of the user key and the commit timestamp. And we store, we actually store quite a bit more metadata than this, but the important thing that we store is the start timestamp. And then we have the lock column family. Now, the lock column family is different from the other two because the physical key is the same as the user key. We don't store a lock per timestamp. Either a key is locked or it's not locked. We don't lock at a particular time, and that's really important. We store some metadata in there. We basically want to be able to point at the primary key where we save like a bunch of information about the transaction. We need the start timestamp to identify the transaction, time to live. There's a whole bunch more metadata because of kind of various optimizations, implementation details, whatever. Okay, so just to summarize again, we have these 3 column families. Default column family stores the actual user-facing values, and we index by the user key and the start timestamp. The write column family stores whether whether a transaction has been committed, essentially. We'll see how. And again, it's a combination of the key and a timestamp. This time it's the commit timestamp, not the start timestamp. And then we have the lock column family, which essentially lets us lock keys in the nodes. Okay, so given that, now let's have a look at how these actions happen. So pre-write, so if you remember back to how the transactions work, this is the first phase of the commit protocol. And so we're going to have a request to pre-write such and such a value to such and such a key. It's actually usually going to be like a range of values for a range of keys, but details. So the first thing we have to do is we have to check to see if another transaction has written data since we since we started our transaction. And if it has, then that means that our transaction's out of date. And if we were to write, there would be a write conflict. And in that case, we have to fail writing and roll back the transaction. Then we check the lock column family. And if the key is locked, that means another transaction has a lock on the key we want to write. And so obviously the current transaction can't write it. So again, we have to give up on the transaction and roll back. Assuming that it's not locked, then we write a lock for our transaction, which means that we've locked this individual key. And we can then write the value into the default column family. Now, note this is pre-write, so that value that's in the other column that we've written into the default column family is not visible to other transactions. It's stored in the database, but it's not visible yet. And then we have the commit action. So the first, this means that all the pre-write actions have succeeded and the client has sent us a commit message. And so the first thing we have to do is check the lock. And if our transaction doesn't hold the lock, that means that an error has happened. Maybe the transaction timed out, maybe the node restarted and we lost our lock, whatever. So it's possible that commit fails, but in it's sometimes recoverable. Assuming that it is still locked, that we still have a lock on this key, then we basically we write the commit message into the right column family. And so at the commit timestamp and the key that we're interested in, we write the start timestamp, which identifies our transaction and and this marks that the transaction is committed. Once that's been written to the right column family, then this transaction on this key is done and we can remove our lock. If the transaction failed, if one of the pre-write messages failed, then the client will send a rollback message instead of a commit message. And in this case, we can delete the value that got written into the default column family. We're not going to need it anymore. And then we have to write kind of like a rollback tombstone into the right column family. You might think that if a transaction is rolled back, then it should just completely disappear. But it's a distributed system and a message could get lost and then delivered after the transaction has already been rolled back, trying to like pre-write the key again. And so to prevent that kind of situation, we have to have we have to store the fact that we rolled back the transaction. And then again, like once we've written into the right CF, then we can delete the lock that's in the lock column family. Notice that we don't have to check the lock before we start the rollback. Even if the lock were missing, we still want to roll back our transaction. So if the lock's not there, we don't need to delete it, but it's not an error. Okay, there's just a question in the chat. Does it mean that you have a notion of transaction limit duration time? I mean, your lock has a time to live if the client's failed. Yes. Every transaction has a timeout. That's essential for kind of being able to recover from like the client failing or a network partition between a client and the server. It's quite interesting. For very large transactions, you might otherwise exceed that time, and so there's a mechanism to extend the timeout. But there's always a timeout. Okay. Okay, so that's kind of like writing to TiKV. How do we read something? Well, we start off by looking at the right column family. So we know we want to read a particular user key, and we know we want to read at a given timestamp. So first of all, we just look for that key at any timestamp, and assuming we find that, then we kind of scan through the various keys that are available for that user key to find the most recent non-rollback entry where the commit timestamp is older than the timestamp at which we're trying to read. Okay, that's quite a mouthful, but if you cast your mind back to the kind of like the snapshot diagram of reading the most recent write, that's basically what's going on here. Once we found that entry in the right column family, that means that we found a transaction that was committed and is the one that we should write to. And so we can read the start timestamp of that transaction from the right column family. And then we can use the combination of the user key and the start timestamp to look up the actual value we're after in the default column family. Ooh, So that's the transaction algorithm. It's a lot. It's a lot to try and explain in just a few slides. So I'm sorry if I've kind of not been as clear as I could be. Does anyone have any questions about that? Do you use the column family to keep history of values? Yeah, so as I've described it, the combination of the right column family and default column family keeps a history of every value written for the keys. This history is not kind of user visible, right? So or at least in TiDB, it's not. There's nothing stopping you using TiKV in a different way. So yeah, you have a complete history of the values, let's say there's another question. So do you have a limit for size of history? There's not a limit for size, but there is a limit for time. So basically we have a garbage collector, which deletes kind of like transaction data that's older than a certain time. I'm not actually sure what the magnitude of that time is off the top of my head. And that answers the other question on chat as well, which is how do you eliminate old data, which is Tombstone, is you have this garbage collector process that runs asynchronously and basically deletes old data, whether it's a committed transaction that's been overridden by a more recent transaction, or whether it's a transaction that's been rolled back. Once it's old enough, then it gets garbage collected. Okay, any more questions about the transactions? Okay, cool, I'll carry on. So there are a huge opportunity for optimization of the transaction system. So I've described kind of like the default implementation, but it's actually very rarely used nowadays. Pessimistic transactions are a variation that's usually more efficient, where you lock keys as you build the transaction up, you lock keys in advance, which means that when you come time to pre-write, you have all the locks already, and so you're much more likely to succeed. Like you'd only fail if there was a network partition, rather than failing because another transaction raced you and won. There's async commit, which is a really interesting optimization that it's worth me showing you a sequence diagram for, and I'll do that on the next slide. There's optimization for small values. So if you've got very small data, rather than write it into the default column family, you can write that directly into the right column family to save this indirect lookup. Obviously, this is only worth it if the data is small, or you'd have to end up copying it around a lot. And there's lots of kind of like pipelining optimizations you can do, and so on and so forth. There's really a lot of interesting optimizations to the transaction system. And there's a question, how many instances of the Oracle time server does the system have? It's usually a small cluster of PD nodes, even when it's a large cluster of TiKV nodes. In theory, so even if no matter how many nodes you have in your PD cluster, it's kind of like a single point of access, and therefore a single point of failure. But in practice, this is not an issue. Like, because literally all you're doing is asking for a timestamp real quick, like it basically never becomes congested. So even when you've got kind of like tens of thousands of TiKV nodes and kind of millions of transactions like going on, contention, it basically never happens for the timestamps. And of course, sorry, and you don't have to ask for every timestamp, right? Like, but there's like a leasing system that lets you batch timestamps out to clients. There's all kinds of kind of like optimizations that happen so that in practice it you don't have contention on the timestamp servers. So curious how the timestamp server returns monotonic values. the timestamp doesn't mean we use Raft for PD. We actually use etcd. PD is implemented using Go and using etcd to ensure consistency between the nodes. Basically because it's not a performance bottleneck, because it's not a performance bottleneck. It doesn't have to be like super high performance like TiKV does. And yeah, like returning monotonic values is, you know, you just keep adding one. Essentially, like it's not kind of like super sophisticated. That's not doing it justice. It's a lot more sophisticated than that, but it's not too bad. And there's another question about how you benchmark for the transactions. So you can do a lot of micro benchmarking, right? Like you can set up on your development box, you can have like multiple logical nodes, and that cuts out the network overhead, but still kind of like gives you the disk IO and CPU and memory overhead. So that can be pretty useful. You might even run like micro benchmarks just on the code that's being run, because you need to make sure that kind of like, you know, each small bit of code is fast. The best thing to do, of course, is just to set up a cluster and time it. Like you can't beat that. And there's a question about, is it correct that only one of the PD server is a leader and the server applies to all queries? I don't think that's how it works. I believe that you can access more than just the one node. So there's one node which is kind of like ultimately responsible for monotonicity, but like the different servers in the clusters can be kind of like gateways. I don't know enough about the PD implementation to tell you how it works though. Okay, so that's a big question, and I'll come back to that in a couple of slides' time once we're kind of out of the weeds with the details. Okay, so async commit, I think is really cool. So if you cast your mind back to the two-phase commit protocol, like after we've got all the pre-writes back, then the transaction succeeds, right? So that's the red arrow on this diagram. Like at this point, the transaction is guaranteed to succeed, but we have to wait until we write at least one commit message to a node. So that's a network round trip before we can return success to the user. So async commit says, well, if it's guaranteed to succeed, let's just tell the user it's succeeded. Which works really well, except that you don't have an opportunity to ensure that the right commit timestamp is written. And so there's a huge amount of work that goes into synthesizing a commit timestamp rather than relying on getting one from PD. Oh, sorry, it's two network round trips, one to PD and then one to the node that you're actually committing. And also recovery gets really complicated. Because you don't have like the single point of failure, single source of truth for a transaction. Like if you look at the primary key and the transaction has not been committed, well, the transaction may still have been committed according to the user. So you have to kind of reconstruct the state in the recovery process, and that's really complex. But it's worth it because you get to shorten the latency on every single transaction significantly. Okay, that's the last thing I want to say about the transaction systems. So if you cast your mind back to kind of like the architecture, region is replicated across kind of like multiple TiKV nodes, and we use Raft to do that. Raft is a consensus algorithm. TiKV has a custom implementation of Raft written in Rust. It's not using kind of like an off-the-shelf one. Raft is a really beautiful algorithm protocol. Call it what you like. It's also very complicated, and I'm not going to try and explain it here. The Raft paper is really good, and if you're at all interested, I recommend you read it. And there's a bunch of good write-ups in various blog posts as well. Basically, the way Raft works is that there's a leader. Wow, that was quick reference with the Raft paper. Nice. The way Raft works is that kind of there's a leader and replicas, and the leader is a source of truth. Basically, consensus just means you report what the leader says. Where it gets complicated is when you need to get a new leader, and you need to make sure that the previous leader has actually gone. It's just not just temporarily unavailable or whatever. And so you have this very complicated protocol for electing a new leader. And as I say, it's a really nice algorithm and worth studying. Just like transactions, there is a whole bunch of opportunity for optimizing Raft. So there is so many different kinds of batching you can do, so that we're never just kind of like committing a single change to the Raft log. That would be really inefficient. We have to batch all these changes together. Another optimization is follow a read. So rather than both reading and writing to the leader all the time, you always have to write to the leader, but you can, as long as you know that so because we're using MVCC, we never actually overwrite data, except for the locks, I guess. We only ever add new data. So you don't need to check that you have the most up-to-date data. You just need to check that the server has been, or the last time the key was updated, you have the most up-to-date information, and then you're able to read from the followers. So this is a really neat little optimization. Okay, and finally, the lowest layer here is, so we've talked about like transactions, which is how the client talks to multiple regions. And then we've used Raft to distribute a region across multiple TiKV nodes. And then finally, on any individual TiKV node, we have to reliably persist data to disk, okay? And to do that, we use RocksDB. So RocksDB is a key value store. It's just off-the-shelf software, essentially. Like, we don't customize it very much, and it's a key value store that does single node storage, and it does it really, really well. It's really kind of like state of the art for doing kind of like single node storage. If you're interested in kind of like database implementation stuff, it's a log structured merge tree implementation, rather than the kind of more traditional B tree implementations. It's really good. It's very high quality. The only kind of like significant change TiKV makes is there's this project we have called Titan, where large values are written outside of the LSM tree nodes. They're written kind of like separately on disk, and that means they don't have to be moved around and reduces write amplification. This was based on a research project called WhiskKey, and it's pretty cool. But that's basically the only way we customize RocksDB. And this is a much nicer way of writing the data to disk, rather than kind of like running our own buffer pools and having to deal with fsync and all this kind of nonsense. Okay, that's the whole talk. There was one question. Okay, yeah. So while this is all rather complicated, it also seems rather elegant. I agree. I thought it was when I was working on it. What are kind of comparator systems, and how does the performance compare with them? That's a really great question, and probably what I'm not kind of like best equipped to answer. I would say there are lots of other systems around that do kind of similar things, and they generally have so one big architectural difference is whether you want to kind of have this layer where you have a separate stateless SQL layer and the stateful key value layer. Some other systems kind of put that all together so that kind of like you're running kind of SQL and kind of distributed storage together. That's probably better for performance. You can see that we get close to that by using the coprocessor, but it's much more complicated. There are various kind of different systems have different optimizations that they do on the basic kind of transaction algorithm. There are many systems that try and kind of like avoid these things altogether, like by doing manual sharding and basically kind of trying never to have transactions, never to have conflicts between transactions, but leaving it up to the user, or having kind of like a transaction server, which is basically a single point of failure for the system, so it's not as kind of like nicely distributed, but can be kind of like much quicker. As you can probably tell, I don't know any of these systems in enough depth to really talk about them, and they have various different performance characteristics and also like trade-off between kind of performance of the system versus complexity. That's probably not a great answer, but it's probably as good as I can do at the moment. Okay, so there's another question about any specific optimization TiDB did for OLAP. So yeah, like there are lots, probably kind of like the biggest optimization and the one that's kind of like the most high level is that there is an alternate backend to TiKV, which is essentially a column storage engine rather than row storage. Column storage generally is much better for analytics type queries, like the Spark style queries. And it's the way that it works is really neat, actually, in that it's done as an extension of Raft. So when Raft replicates data across rows, it treats the column storage engine as just another node that it's going to replicate to, and therefore kind of like keeps the column storage up to date. There's actually a paper on TiDB which was published 2020, I believe, maybe it was last year, which describes TiDB as an HTAP database and describes this neat way that the column storage engine is used. So I would recommend reading that paper if you're more interested in that kind of thing. Yes, this SPLVM one, that's the one. Thanks for the link. Okay, does anyone else have any more questions? I think we have gone over time slightly, but I'm happy to answer any more questions if anyone has them.
Yeah, we have maybe we can have maybe 10 minutes for Q&A. Was a lot of knowledge to be unfolded in a database talk. Nick,
yeah.
I have a question about the transactions. So the whole transaction algorithm you mentioned, is it for read-write transactions, right? And does it have any particular optimization for read-only transactions?
Well, so read-only transactions don't need to be committed. So, so if I flick back to the sequence diagram, so a read-only transaction, you basically don't need to do so the first stage, which is in blue. So on a read-write transaction, you execute the reads as you go along, buffer all the writes, and then you start the kind of transaction, the two phases of the commit protocol. Well, if you've only got reads, and no writes, then you just return success at that point, and you don't need to do any of the commit stuff at all. In fact, if you know ahead of time that you only need to read, you don't even need to start a transaction. You can just use the, I mean, you might want to get a start timestamp from PD, or you could just use the most recent one that you have locally if that's good enough. And then you can just make your reads outside of a transaction.
And it's optimistic transaction, so we don't acquire a read log for read-only transactions.
Yeah, that's correct.
Got you.
Yeah, so there's a couple of questions. So what itch did TiKV scratch? Why build yet another DB? So way before my time on the project. So I believe the answer is simply that they figured they could make a business doing so. The founder's background was they were working in some kind of like large corporate places in China, working on database stuff. At that time, so this would be about 2015, new SQL didn't really exist outside of Google. So they read the Spanner paper and they were like, well, actually we could implement this. We could have a database that was SQL compatible and had these strong transactional guarantees and was distributed and scalable, and we can actually make this ourselves. So let's do that and make a business around it.
I guess over the time, people just find transactions to be very useful thing to have.
Right, like transactions have proved to be very useful over time. And I think kind of like if you now there's quite a few databases in this space. I mean, still not very many, it's still like a handful, but in 2015 there were not. And I think there was literally kind of Spanner that was used inside Google and wasn't kind of like sold as a product to anyone outside, or you had kind of the NoSQL databases where you lost the transactional guarantees and you lost the SQL, or you had kind of the traditional kind of single node databases that have been hacked to work on multiple nodes and where you had to kind of like do the manual sharding and so forth. So there was definitely kind of like at that point a gap in the market that the founders identified. Okay, and then so if we use TiKV in a geo-distributed environment, how many WAN RTT will you have in the worst case? So this is also a really interesting question. So so basically it depends how you split your data between data centers, but kind of like the worst case is you have a query that doesn't fit the patterns that you are anticipating. And then the next question is, what data center is your PD cluster in? And I believe, like when I left, there was work to make PD work better across data centers. No idea about the current status of that. So I'm not actually sure whether you have to make a round trip between data centers to ever get the timestamps. But I mean, like worst case, let's assume like you did, then basically every single one of these, so look at the sequence diagram that I've got on the screen at the moment, and every single one of those could theoretically be a call between like data centers, right? Like if you've mismanaged things so that the TiKV nodes you need are separate from the client, and like the PD stuff hasn't worked out, so you need to ask for the timestamps there, then there's going to be kind of like lots of calls. I would say that the way that TiDB the way I would set up the clusters is that like you would always have the nodes in a raft cluster in the same data center. So your the propagation between nodes in a region is always going to be within a data center. And so it's only the arrows in their sequence diagram that are going to be between data centers, not also the ones to do the raft replication. But that but I guess like if you were really paranoid about like a data center burning down or something, you might want to replicate across data centers. I'm not exactly sure like how people might configure that. So I would say so also shown on this not shown on this diagram is that you might have to ask PD for the physical address of a TiKV node given a key. This is all cached locally, so you don't have to ask this for every transaction. But you know, if data is moved from one node to another, then you might need to refresh that cache. So you've got a round trip to get a start timestamp. You've got a round trip to find out where a TiKV node is. So that's kind of like 1 plus n, where you're talking to n nodes in a transaction, plus a round trip to each TiKV node, presumably. And you might have to make multiple round trips if you've got multiple reads. So 1 plus n, where n is the number of reads. So that's just for your reads. And then 1 round trip for each pre-write. So that's 2n plus another round trip to PD to get your commit timestamp, and then a final round trip to a single node to get your to commit the primary before you return success. So I think that's 3 plus 2n plus n round trips, which is quite a lot. In theory, and probably in practice, you could batch the request for a timestamp. No, you can't. Sorry, I was going to say you could batch the request for a timestamp with the location of the TiKV nodes, but you don't know in advance which TiKV nodes you're going to read. So that would be a problem. So yeah, in theory, you can have like a lot of network traffic for a single transaction. In practice, by doing good layout of data and by doing a lot of caching, you don't have too many round trips in practice. Okay, sorry, that was, I'm not sure whether that was a useful answer or not, but it was fun to count. Any other questions?
If no one has a question, I will ask one. So Nick, what particular challenge when you are working at TiKV and using Rust to write a database implementation?
Sorry, what could you repeat that?
Yeah,
question
so
again?
the question is, what particular challenge did you face for using Rust to write a database implementation?
Okay. So I think one of the more, so I mean, I had a lot of experience with Rust before I started implementing databases with it, and so kind of like I think a lot of people you know would face challenges that kind of I had already kind of like previously come across. Specifically things that are difficult as the immaturity of async. And I think we're in a much better place now than we were kind of like 3 years ago when I started working on TiKV, but it's still not great. So especially when you're doing stuff with kind of asynchronous iterators, which used to be called streams, things get difficult. So I think, yeah, the kind of immaturity of async programming was probably kind of like the biggest challenge.
Was the async library improvement the #1 goal you have right now?
Yes.
Working at Microsoft.
Yeah.
That's great.
I mean, there's I have a bunch of other stuff going on, but yeah, really kind of like improving the situation of kind of like the async ecosystem, I think is my top priority.
All right. Does anyone have other questions? Sorry about being a little bit over time today.
Yeah, sorry about that. These talks always take longer, like
Exactly.
in real life than when you rehearse them.
If you think about it, how crazy you have to talk about unfold the whole implementation of a database in maybe 2 hours. All right. Thanks everyone for joining today's event. For next week, we are going back to the lectures in CMU 15445, which is the database management system course. And again, the whole meetup in the future will be presented in Chinese. I know it might create some barriers for those English speakers, but we do have a new events coming, and that's called the Database Internals Meetup, and do check them out. And thank you very much, Nick, for today's talk. It's truly impressive. And thanks everyone for joining today's event. We'll see you. Again, the whole event is recorded and will be uploaded to YouTube.
Thanks very much for inviting me, and thank you everyone for attending. And yeah, if anything's interesting, please do get in touch. I got my contact details back up on the screen there. Thanks everyone.
All right, I'm going to start recording.